So now we will be dealing with boundary conditions. There are two types of boundary conditions. One is electrostatic boundary condition and the other is magnetic boundary conditions. So this boundaries, in the case of electrostatic fields, it may be classified into three. Dielectric boundary. Second one is conductor dielectric boundary. The last one is conductor and free space. So in order to determine the boundary conditions, we are dealing with two equations. That is, the first equation, which is called closed line integral E dot dl is equal to 0, and the second is surface integral E dot ds is equal to Q enclosed. So now you can see the electric field intensity, we are considering it to be divided into two components, namely ET, that is a tangential component, and En is the normal component. Similarly, the electric flux density D is also consisting of two parts, namely dt, that is a tangential component of electric flux, and Dn is the normal component of electric flux. So we are considering the first case, that is dielectric boundary conditions. It means the electric field is moving from one dielectric to another dielectric. So let epsilon 1 be the permittivity of the first dielectric and epsilon 2 be the permittivity of the second dielectric. So now we can see the figure, first figure, that is for determining the tangential component of electric fields. So you have the first medium epsilon 1, and this is the second dielectric epsilon 2. E1t and E1n are the normal components of the first dielectric medium. Similarly, E2n and E2t are the tangential and normal components of the second dielectric medium. Okay. So for the analysis, we are considering a closed path A, B, C, D, A with length delta W and width delta H. And we are writing the two equations, that is E1 is equal to, you can write it as vector sum of E1t plus E1n, and the vector E2 can be written as E2t and E2n. Okay, so you have written the two vectors E1 and E2, where E1 is equal to E1t plus E1n, that is the sum of the tangential component and the normal component. Second is E2 is equal to E2t plus E2n. Now apply the law circulation E dot dl is equal to 0 to the closed path A, B, C, D, A. Okay, and we are going to assume one thing, that is delta H, that is this length, is very small. Okay, so when you apply E dot dl is equal to 0, you can see apply to the path so that I can zoom it for you. So E1 into E1t into delta W, that is this path, in this path we are going to add the circulation. So E1t into delta W. Okay, so this closed path is lying in the boundary between the two surfaces. So E1t into delta W plus, now this path you can see it is divided into two, it is lying in the two mediums, so let us consider it as this point is a midpoint. So E1n, that is a normal component. Along this line it is perpendicular to E1t, so it is the normal component we have to take. So E1n into delta H by 2 minus, you are giving minus sign because it is opposite to the direction of E1n. So minus E1n into delta H by 2. Then again you are coming downwards. At this portion, the component of electric field is E2n. So it is minus E2n into delta H by 2. Okay. Then coming over from C to D, it is minus E2t into delta W. Okay. Then again from D to A, when you are going, it is moving from second medium to the first medium. So it is E2n plus E2n. It's the same direction as E2n. So E2n into delta H by 2 plus E1n into delta H by 2. That is written in equation number 3. You can see, okay, everything that is equal to, that is surface line integral E dot dl is equal to 0, that you have expanded. So that's all these terms is equal to 0. Now you can see there are equal and opposite terms over there. That is E1n into delta H by 2, you have a plus term and a minus term, so you can cancel. E2n into delta H by 2, that you have a plus term and a minus term, you can cancel it. So what you get at the end is E1t into delta W minus E2t into delta W is equal to 0. On simplifying this, cancelling the delta W on both sides, you get E1t is equal to E2t. This means the tangential component of electric fields are same at the boundary, or you can say the tangential component of electric field is continuous at the boundary. You use the term continuous. Please note, it is important. Tangential components of electric field is continuous at the boundary. So this is one of the important derivations here. And now moving on to the next step, we also need to analyze about electric flux. So how is electric flux related to electric field? D is equal to epsilon E. Okay, this D is also having two components, that is dt and dn. So E1t you can write it as d1t divided by epsilon 1, and E2t you can write it as d2t divided by epsilon 2. So from the above relation that we have derived, equation 4 can be rewritten as, instead of E1t you can substitute as d1t by epsilon, and instead of d2t you can substitute as E2t you can substitute as d2 by epsilon 2. So you get the equation d1t by epsilon 1 is equal to d2t by epsilon 2. So you can see d1t and d2t are not equal, but they are having a ratio in between them. You can write d1t as, taking the epsilon 1 to the right hand side, d1t is equal to epsilon 1 by epsilon 2 into d2t. So you can say that equation 5, this is equation 5, so you can say that the tangential component of electric flux is discontinuous, or it is undergoing some change at the boundary. It is discontinuous at the boundary. In this figure, we need to determine the conditions about the normal components of electric flux density as well. So for this, we are considering a cylindrical closed surface. This cylindrical closed surface is known as a pillbox, P-I-L-L-B-O-X, pillbox. Okay, so you can see, similar to the electric field, we have drawn a diagram, vector diagram. D1t is a tangential component in the first medium, D1n is a normal component of electric flux density in the first medium, D1 is a net electric flux density in the medium 1. Okay, you can see a mistake there. I think I have written E epsilon 2 in medium 1, please make it as epsilon 1. Now coming over to medium 2, D2 is the electric flux density in medium 2, D2n is a normal component of electric flux density in medium 2, D2t is a tangential component of electric flux density in medium 2. And you can see the surface area, normal surface area is delta S, and delta H is the height of the pillbox. The theorem, surface integral d dot ds is equal to q enclosed to this pillbox. So you can write from the top surface the normal component of electric flux. In medium 1 it is d1n. So d1n into delta S. Okay, that is from the first medium. Then you have from the bottom medium you have d2n. Okay, that is going downwards opposite to minus d2, so minus d2n into delta S. Okay, the other two terms you can neglect, the components of d1t and d2t, because your delta H you are assuming or you are neglecting it. Okay, so that is equal to Q enclosed. What is Q enclosed? If rho s is a surface charge density, the net charge enclosed will be rho s into the surface area delta S. So d1 delta S minus d2 delta S is equal to rho s delta S. So cancel off the delta S from all the sides. You will get d1n minus d2n is equal to rho s. Okay, where rho s is a free charge density at the boundary. So you can see from equation 6 that the electric flux density normal component is discontinuous at the boundary. Okay, but assuming there is a special case, if this charge density at the boundary is 0, this normal component of electric flux density becomes continuous. That is, if rho s is equal to 0, d1n is equal to d2n, which means electric flux density is continuous across a charge-free boundary. Okay. Similarly, you can write d1n as epsilon 1 E1n is equal to epsilon 2 E2n, or you can write E1n is equal to epsilon 2 into epsilon 1 by E2n, or from equation 8 you can say that the normal components of electric field intensity is discontinuous at the boundary. Also, next topic, the same thing is the refraction of electric field at the interface of dielectric boundary. Now, what do you mean by refraction? In case of light rays, we say refraction means while a light ray is traveling from one medium to another, there is bending of light rays. Similarly, electric field, magnetic field, etc. are electromagnetic radiations. So when they travel from one dielectric to another dielectric, there is refraction or bending. So we are considering that E1 is making, electric field in medium 1 is making an angle theta 1 with the normal or with the perpendicular, and E2 is making an angle theta 2 with the normal. Okay, we have already derived that E1t is equal to E2t. Okay, so you can see if theta is the angle, E1t can be written as E1 sin theta and E1n can be written as E1 cos theta. So since E1t is equal to E2t, E1 sin theta 1 is equal to E2 sin theta 2. So you can mark it as equation 9. And next, we have also derived d1n is equal to d2n for a charge-free boundary. So you can write d1n, you can write it as E1 epsilon 1, E1n is equal to epsilon 2 E2n. Okay, and E2n and E1n you can write it as E1 cos theta 1 and E2 cos theta 2. So epsilon 1 E1 cos theta 1 is equal to epsilon 2 E2 cos theta 2. Now what you need to do? You need to divide equation 9 by equation 10. By equation 10, you get tan theta 1 by epsilon 1 is equal to tan theta 2 by epsilon 2. Substitute for epsilon 1 as epsilon 0 epsilon r1 and epsilon 2 as epsilon 0 epsilon r2. Substituting that, you get tan theta 1 by tan theta 2 is equal to epsilon r1 by epsilon r2, which is a very famous equation which you would have studied. And it is known as the law of refraction of electric field at the boundary. This is very important, law of refraction of electric field at the boundary. So you can see that an interface between the two dielectrics, it produces bending of electric flux lines, which is as a result of unequal polarization. Please note, it is because of the unequal polarization charges that accumulate on the opposite sides of the interface. Thank you.